Hello everyone, my name is Zhenhao Zhao. I'm a graduate student at the George Washington University. For this presentation, Jonathan, an undergraduate student, and I will introduce our work about using computer vision technique to assist UAS landing. The title of our paper is Vision-Based Perception with Safety Awareness for UAS Autonomous Landing. The use of small unmanned aircraft system (UAS) is promising for the last-mile package delivery. Commercial small UAS have become more and more automated in executing predefined flight plan and landing on well-managed landing pad. However, to achieve higher level of autonomy during off-nominal landing, a UAS needs to recognize landing scene reconfiguration such as moving or static obstacle near or on the designated landing pad. It will improve the awareness and the safety, prevent risks. In this study, we proposed a robust, real-time deep learning-based safe landing perception algorithm. The total algorithm includes three main parts. First of all, it will detect the potential obstacles like the pedestrian and cars, and then it will identify the landing pad. Finally, it will check the potential obstacle position to make sure they are on or near the landing pad. The first part of the algorithm is detecting the potential obstacles. We should develop a deep learning-based approach for pedestrian detection and tracking to aid in autonomous landing of a UAS. It's a dynamic and complex environment. The traditional rule-based algorithm can't solve it very well. Therefore, we choose the deep learning-based function. To reach the higher accuracy and inference speed, we compare the two models, ULOV5 and RetinaNet. Our training dataset is VS-June. We did transfer learning on it. The dataset has about 7,000 static images from 14 different cities, including about 34,000 bounding blocks. The dataset contains 11 classes and also include image quality information like truncation and occlusion. Here is the structure of the RetinaNet. It uses ResNet as backbone to extract the feature map and then analyze and combine the extract feature map by a feature pyramid nets. Finally, by using two subnets, one subnet for classification and one subnet for localization, we can get the final output. General structure of the ULOV file is pretty similar to the RetinaNet. They both use a backbone network to extract feature of the original input, then a next structure to use to combine and analyze the feature extract from the backbone network. Finally, a head structure is used to integrate the output of the NAC and make the final detection. The focus first introduced in the RetinaNet is also used in ULOV file. The key difference comes from the technical details. Firstly, compared to the ResNet 50, the two bottleneck CSP structure of the ULOV file have less layers and more efficient. Next, the backbone of the ULOV file also uses the spatial parameter pooling layer to balance the extraction of the global feature and the local features. In the final output head structure, ULOV file uses one network to directly output the classification and the bounding box localization. Here is the result of training process. The left 10 graphs is a loss decreasing and perception increasing graph of the ULOV file, and the red 2 graph is for the RetinaNet. As we can see, both of the model become better and better as the training process. The accuracy indicator going up and the loss indicator going down. Mean average perception (MAP) is a metric used to evaluate object detection model. When the MAP is higher, the model should be more precise. It worth noting that the MAP of ULOV5 is slightly higher than that of the RetinaNet, with the best epoch.
Here we show the results of both YOLO V5 and RetinaNet on each frame of a self-collected video. The videos show the bounding boxes of detected objects overlaid on the original footage. The output of RetinaNet is on the left and YOLO V5 on the right. Both models were able to detect all the cars and pedestrians in the scene. The footage was captured by a DJI Mini 2 quadcopter and was recorded in 4K resolution at 30 frames per second. We use confusion matrices to show the classification patterns of predicted classes versus the ground truth. The result is as expected since most predictions fall along the main diagonal. This indicates that the prediction classification matches the ground truth classification. Note that there are many more pedestrians and cars than other classes due to the high class imbalance of the dataset. The model did misclassify other vehicle types as cars, including vans, trucks, buses, and motorcycles. We found this was not a significant issue since all vehicles will be regarded as obstacles by the safety detection algorithm. Here is a comparison of the inference speeds of RetinaNet and YOLO v5 on a 14-second video on different hardware platforms. For our testing, we used our lab workstation with a RTX 3080 GPU and an NVIDIA Jetson Xavier NX. We found that YOLO v5 was an order of magnitude faster than RetinaNet on both platforms. Based on this result, we decided to use YOLO v5 in our final safety detection algorithm. We used Aruco markers to build, detect, and track the landing pad. The Aruco library is based on OpenCV and enables the detection of various tag dictionaries. We can also get the distance and angle information from the camera to the Aruco marker. Here we show how we build and detect the landing pad using 4 Aruco markers positioned in a rectangular pattern. We draw a bounding box around the outside perimeter of the 4 detected Aruco markers, and place a circle in the center to indicate the center of the landing pad. Our landing pad safety checking algorithm detects if there are any potential obstacles on our landing pad. First, the algorithm uses one of the deep learning models, namely RetinaNet or YOLO v5, to detect all the obstacles in the scene. Next, the landing pad is detected using the Aruco library. Then for each of the detected objects, we check if there's an intersection between its bounding box and the landing pad. If any region of the bounding box overlaps with the landing pad, the flag is set to true, indicating that there's a hazard on the landing pad. Here is the result of the safety detection algorithm on 2 images. On the left, both a person and a landing pad is detected from the view of the UAS. However, the person does not overlap with the landing pad and the flag is not set. In the frame on the right, the person is detected within the landing pad, so the flag is raised to indicate that there's a hazard in the landing zone. The output of the safety detection algorithm can be passed to a planning and control module where a decision would be made whether to pause or abort the landing. This work presents a major part of our research team's continuous effort to build a full-stack autonomous landing demonstration. Thank you for your time and attention. We look forward to answering any comments or questions.